Hi, good morning. How are you? I hope everyone is fine. Previously, I already upload three main video. The first part is describing what we are going to learn in these sections. Second, what actually some restrictions that will be imposed for the industry, especially if you look current scenario in terms of resources, fees, and also joint of ordering. And the last one is how we can apply it on the Lagrangian expressions in order to solve the issue. So since this is multi-items, so we are starting to go for a complex model. And this is the beginning how the software is come into the picture when solving thousands of items in the industry or organizations. So we're coming to deterministic multi-item inventory model where we need to have a special care because of the complex model. So when we say multi-item is the materials management involve many items and transactions. And in order to mostly of the research only focus on the ABC items, which just indicate where managers should concentrate or focus. But in the long run, we need to also determine what will going to happen and when we need to order and how much need to order for class B and C items. So here we are using advanced techniques such as meta heuristics and also Lagrangian expressions. So when we are saying multi-items of single source, it means the placing order for several items provided by the same source can result in significant inventory cost saving. This is usually that like how company is going to order. Example, they are order for China for few items. So it means that is it good to do a joint EOQ or back order or joint back order or back ordering, okay, based on economic dollar value. The main thing in these sections of lecture is basically how we're going to do minimize the total cost and also increase the total profit by doing a lot of savings when we doing joint ordering, or we have some restrictions in the space or place order on the periodic basis or singular period. So deterministic multi-inventory items, there are two types of cost items. One is the unknown cost structure and non-cost structures. For your midterm, basically I will involve with model with known cost structure. Involving of joint orderings, multi-orderings, specific orderings with some restrictions, and also with some meta-heuristics methods. So this is the way how I try to modify it, where multi-items can divide it into two, known and unknown, with limitation and without limitation, in order to minimize the total cost, total order, total sum of the restrictions or space. Some organizations in some situations have not developed cost structure related to inventory control, but they still wish to minimize total cost of inventory. This may due to because they don't have any basics or fundamental knowledge about inventory control. There are many critical situations such as now what we are going through now, where organizations may need to take immediate action to improve the situation without considering the structure of the cost. And as far what we know now, is very hard to get raw material from China. So a lot of companies need to shut down their company, although they no need although they have opportunity to get more profit during this period. So first, we are going to minimize total carrying cost while keeping the number of order fixed, and minimize the total number of order while keeping the inventory. Basically, this type of methods I will just let you all guys to go through, because I will go to more important part, which is we will be talking about known cost structure. Basically about known cost structure, we have with limitation and not limitation, and here we still reconsider about total cost of order, and also cost of inventory, which we still look on the demand, ordering cost, holding or carrying capacity costs with Q optimals. Let's go for EOQ and multi-items. Most inventory systems stock many items, sometimes thousands of items. Let's say we took example of laptops. In order to produce a laptops, we need at least thousands items. So restrictions may be imposed. This is usual, like how we already start to talk previously, because we sometimes will have a limited resources, limited space, limited money or value of money, and limit of labor. We need to optimize. That's the main point here. We need to optimize whatever that we can save, so that we can get more profit uh, with less cost. And restrictions may be imposed, limited on warehouse capacity, upper limit on the maximum dollar investment, number of orders per year, and so on. And actually, basically, all of these items will actually cover after covering nonlinear programming, which is we are using Lagrangian expressions. When and if you look in the books of reference books, not many books talk on multi items. Maybe far that I know, most of the books that talks on storage limitation with only a surface information is on Book of Taha. Only Book of Taha. So where they mention that deal with more than one items, no shortage. And do remember, we're still not going for a shortage. Our assumption still no shortage, and items are competing for limited storage. Here they are do on the storage limitations. And basically, they are using multi-item EOQ, and they compare with EOQ when they order single items. And look here, if you look here, when we have item 1, item 2, and item 3 with all the demand and cost of order plus holding plus total available storage is 25 feet. But now if you look here, we have more than that, which is 11.55 plus 20 plus 24.49 is actually more than 25,000, 25 meters square of units. Then now they want to make sure it's restricted to 25. Here they are using nonlinear program solver or AMPL, which I will try to do with you in tomorrow lecture, in tomorrow tutorial class. And actually here I'm going to explain on how we can do it manually using Lagrangian expressions. So here we have basically 3 steps. The step 1, we compute unconstrained optimal value of the order quantity. If storage is satisfied, it is optimal solution. Otherwise, go to step 3. Step 3, we will have modified denominator. Basically, this is called Lagrangian optimal quantity. Basically, we are using Lagrange multiplier methods. So, overview of nonlinear programming. Many realistic problems have nonlinear functions. Let's go back to our, if we go back to our example of total cost, which is dealing with D over Q over D over Q times C naught plus the IC QJ over 2, where one is denominator, another one is numerator. So both of these one, because not having the same position, we call as nonlinear programming or nonlinear optimization problem. So in linear programming, solutions are found at the intersection, but in non-linear programming, there are no corner point or no feasible solution. So in order to do this one, we need to understand what we have as local and global point. And if you look here, our global point is this one and local point is this one, where solution techniques generally search for high point or low points. Difficulty in nonlinear programming is to determine whether the identifier is a local or global, where we need to use a very complex mathematical technique, which I'm not going to explain here. but we are going for constraint and unconstrained optimization. Okay, let's look. We need to understand this nonlinear programming with multiple constraint optimization so that we can change the inequality, like how I'm explaining the part 3 of the videos previously, which we can convert the inequality constraint to equality constraint optimization, so that equality constraint optimization can be used in multiplier, in Lagrange multiplier expressions. So usually nonlinear programming is very complex and basically have two main methods that usually use. First, list of substitution method, transfer a constraint optimization to unconstrained optimization. Second, we are using Lagrange multiplier. Here we will talk more on Lagrange multiplier. So we are going straight to Lagrange multiplier because when we talk about substitution, they have a lot of limitation. Okay, let's go to the Lagrange multiplier. Used for constraint optimization consists of nonlinear objective functions and constraint. Transform objective function into Lagrangian function. Constraints as multiples of Lagrange multiple are subtracted from the objective function. Consider example, maximum z is maximize x subject to x1 plus 2x2. When we are forming Lagrangian functions, which L equals to the objective function plus with the lambda or minus with the lambda of x1 plus x2 to x2 minus 40. So from here we can do partial derivative as in inventory control previously to find the QJ, and we use the same method here. And as far what you already learned in 251 on sensitivity analysis, here the sensitivity analysis actually is changing the left hand side. And let's go to example limited working capital. Let's say given that there is three items with particular EOQ and QC, and now the total number of the quantity capacity is 17,000. Now let's say the organization have restrictions of the available budget, and now they are saying this budget currently they only limited to 15,000 compared to currently what happened here is 17,000. So how you as a CEO of the company can solve the issue? So we can solve with the method of Lagrange multiplier. Before applying the method, we should solve the total cost function by ignoring the constraints. Otherwise, we can form the Lagrangian expressions. So let's see, the total budget is now 17,120 ringgit, is more than available budget is 15,000. So we can form the Lagrangian expressions where L equals to summation of DICI. DICI means demand times the cost of item plus average inventory plus with the lambda QC minus B. It means this is the constraint, and we just do the derivative as how I mentioned previously. So now it should be getting easier how the work should be done, because it's quite easy, correct or not? And from there we can form the first equations, then form the second equations, and finally substitute to get the lambda equations. So example, this is the model with total QSK is on the cost of order, and also average inventory model, and subject to example here, subject to the constraints, type of constraints. Example, let's say then we form into a Lagrangian expressions, then we derive towards Q and derive towards lambda or theta that refer for constraints. From there we can pick a value for lambda. After we pick the value for the lambda, then we can compute the QJ and also the value of the total cost. We need to repeat 1 and 2 until we form the total number of the constraints. And we can do the same thing not only for that type of constraint but all type of constraint, because this is called generalized Lagrangian approach. So we can do the same thing for warehouse space constraint where Wj is a W. We can do it, and also we can solve all Lagrangian functions. So let's try to do the homework assignment 1 and homework assignment 2, where we are going to discuss more equations and more examples in tomorrow lecture. Thank you.